Okay, so we're going to tackle this problem. There's a few things that we need to do first before we really get into the nuts and bolts of this problem. We're going to, first off, we want to look at what we want to solve for. So it's asking us what's the distance from C to D. And we're going to label these real quick. This is A. Actually, let me label that with a different color. I'll go with black. So this is A. This is B. This is C. And this is D. Okay? So we want to solve for those. A couple of other things I want to write on here just to make sure so it's clear. This is a PT. This is a PT. So these dots are points of tangency. These dots here are points of curvature, so PCs. Okay? So, what we want to do first here is just draw some stuff on here to make sure we know what is what. So I'm going to take and connect the dots between these PCs, because if we connect the PCs and extend them, and then take and connect the PTs and extend those, we will figure out our radius point. Okay? Call that our radius point, RP. All right? So by connecting those, we find our radius point. Now, there's a few things here that we want to take and make sure that we do before we solve for these. We have, it looks like there's a radius of 110 feet here. So my radius on the inside is 110 feet. And it looks like between the two PTs, it's 45 feet. Okay, so I can do that here too. 110 feet and 45 feet. Okay, so I'm labeling all the stuff I know at this point. All right. Okay. So let's take and the very first thing, if we look through what we're solving for, what's the distance from C to D? Okay, so we're looking for this distance. What is the arc length of A to D? So we're looking along the curve here. What's the length along the curve? And then the very last one, or the first one we're going to solve, is what is the arc length of the center line of the public road. So public road, so I want to find the center line. So from PC to PT along the center line, what is that length? Okay, along that arc. So we'll solve for that first. So I'll switch colors here, and bear with me because there's a lot of calculations that are going to happen on this. So I'm going to switch in between this blank page and our drawing as we move forward here. Okay, so let's start. I'm going to start at, we'll say number 1. And we're going to solve for the center line of the public road. Okay, so that's what we're solving for. Center line of the public road. All right, so let's take a little look at our sketch here. I'll slide this off to the side. So what are the things we know here to help us solve for that center line of the public road? Excuse me. So center line of the public road, first off, we need to find I, which is here, okay? In order to find our L. So let's take a look at the formulas that we're going to use to solve for that center line. So we need to find I, okay? We're going to need to find the radius. We're also going to have to find delta, and we're going to have to find the L at the end. That's what we're looking for, okay? So let's see here. the radius. Well, yeah, let's look at the radius first. So the radius equals, and there's no calculations that they have to happen here because we were given the radius. But, thing to pay attention to is we're looking for the length along center line here, okay? So, I'm given a radius at this arc of 110, but I need to be out here. Well, I know that the road width is 45, so in order to find the radius, I need to take 110 plus half of 45. So let's write that out. 110 feet plus half of 45 feet. Okay? In this particular example, this is how we're finding the radius. So the radius is 132.50 feet for the center line of the road. Okay, so we found the radius. Next thing we're going to find, let's find I. Okay, let's find I. All right, so how are we going to find I from this example? Well, it looks like we have a bearing here and a bearing here. From what we know about curves, these tangent lines are always perpendicular to the line coming in, or perpendicular to the radius point. Okay, so this is perpendicular here. Same here. Okay, so we know that if we take 90 degrees plus this, it'll give us this bearing. Okay, so let's take a look at that once. So I have a north 545 west bearing here. So let's take and turn that north 0 degrees, 5 minutes, 45 seconds west. Let's figure out what that is and add 90 degrees to it, or subtract 90 degrees. So what I'm going to do is I'm going to take and go 90 degrees right here to figure out my bearing. Okay. So I actually have to turn that bearing to a southwest. South 0 degrees, 5 minutes, 45 seconds west. Okay, so I'm going to add 90 degrees to that. All right. But what I'm going to do here is I'm going to turn this southwest into an azimuth. So it's 180 degrees, 5 minutes, 45 seconds. Now I'm going to add the 90 degrees to it. So I have 270 degrees, 5 minutes, 45 seconds. Okay? This, as a bearing, is south 89 degrees, 54 minutes, 15 seconds west. And I apologize there, I had to stop because I was a little stuck there, and I figured out what I did. This was actually supposed to be east, so that threw me off. So this number here, if I take that plus that, is actually 179 degrees. Let's see here, we have southeast plus 90. 54, 15, okay? That is not this. So it was all because I screwed up this west, so it's a good lesson learned to make sure that we have the right things. So as I do this, this is changing now too. So this would be 269 degrees, 54 minutes, 15 seconds, which would in event give us this bearing there, okay? So this bearing here is right here. South 89 degrees, 54 minutes, 15 seconds west. Okay, apologize for that little mix up there, but you can see how easy that is to do. All right, so I figured out my bearing there. The next one I want to figure out is the bearing for here, okay? So I'm going to look at this bearing. We have a south 89 degrees, 59 minutes, 50 seconds east. Okay, so that's that bearing, and we're trying to come down on this line here. So let's take a look at how we're going to do that. Okay, so if I take this, I'm going to turn this into an azimuth again, but this time I'm going to whip it as a back azimuth. So I'm going to turn this into a northwest this time. Okay. So let's see how we're going to do that. So it's a northwest. So I'm 360. I want to turn it into an azimuth because it's easier to work with azimuths. So I am north 89, 59, 50 west would be the same as, let's take a look here, trusty calculator. We'll take 360 if I'm turning it into azimuths and take 89, 59, 50 and subtract from that. That is the same as saying, for an azimuth, it is 270 degrees, 00 minutes, 10 seconds. Okay? So what I want to do with this now is subtract 90 degrees. So it gives me 180 degrees, 00 minutes, 01 seconds. Okay? So what is that? Or 10 seconds. Sorry, 10 seconds. 180, 00, 10 seconds. So what is that as a bearing? So this as a bearing then is south, 00 degrees, 00 minutes, 10 seconds west. Because it's over 180, so it's a west. West, it's over 180. Okay? All right, so let's take and populate that on there. This line here now, we just figured it out, is south, 00 degrees, 00 minutes, 10 seconds west. All right, so let's figure out this angle here then. This full angle. Okay? Well, that's easy to do because I already figured out my azimuths of both of those. I have the 269, 54, 15, and I have the 180, 00, 10. So I should be able to figure out that interior angle pretty easily. Okay? So let's look at these. This is a northeast, this is a northwest. If we switch them around, so we're looking at here, okay, so if I'm going from the RP out to A, or RP out to the PC here, we're looking at this angle in here. So this is also can also be considered a northeast bearing, so we're going to flop it around as if we're going from the RP out to the PT. This one can be considered as a northeast bearing as well, but we're going from RP to PC. So what we're going to do there is basically just add these two because they're in the same quadrant. Or no, subtract one from the other because they're in the same quadrant. So we're going to subtract those, okay, to give us our interior angle. So if I take 89, 54, 15, the bearing of that, and 00 degrees, 00 minutes, 10 seconds, and subtract those two, this angle on the inside here should be 89 degrees, 54 minutes, 05 seconds. Okay, it's really tiny, I know, apologize, but this is going to be a huge calculation, so we're going to be making a big mess of this drawing. Okay, so I just figured out I by figuring out that these two were in the same bearing direction. I just subtracted them to get the interior angle. Okay, so our interior angle then, I, is 89 degrees, 54 minutes, 05 seconds. Okay? All right, so we figured out I. Now that we have I and R, we can figure out D. So D is equal to 5729.58 divided by R. Okay? So D equals 5729.58 divided by R, 132.50. All right, so D is equal to, do a calculation quick, 5729.58, 132.5 divide. All right, so this, can't see that real well. This is the answer I get, but this is in decimal degrees. On my particular calculator, I have to change this to degrees, minutes, and seconds, okay? So it is, our D value then is 43 degrees, 14 minutes, 32 seconds. So we have 43 degrees, 14 minutes, 32 seconds. That's D. All right, so we solve for D. Now, what we've been trying to get to is L, the center line length of that public road along the curve. Okay, so the arc length. All right, so let's figure out L. So L is equal to 100 I over D. Okay, so L is 100. My I value is 89 degrees, 54 minutes, 05 seconds, over D, which is 43 degrees, 14 minutes, 32 seconds. Okay, so my L value then, toss up my trusty calculator here. Let's see if I can get it so you guys can see it better. That's not good. Here, we'll put it down here. All right, so the way I stack in my calculator is different than you guys probably will in yours. But all right, so my distance along my arc of my curve, or a curve in the center of the road, is 207.90. Okay, so we got 207.90. That is our answer for the arc length of center line. So this one right here, what is the arc length of the center line of the public road? That is 207.90. Okay, we solved that. Okay, so one down, two more to go. Okay, so I'm going to get rid of this sheet of paper and I'll move to another one. Now we're going to worry about slowly solving the rest of the problem, okay? So now we figured out these few things. We're going to move to breaking this part of it down. So I'm going to add a few more lines on our drawing here. Okay, so I'm going to break this down into triangles now. And we're going to solve for those triangles to get our parts. So eventually we're going to be able to solve for a triangle that gives us this length and also the information to be able to solve for this curve. So I'm going to break this down into triangles to be able to solve it the way I want to solve it. Okay? This will work. All right. All right, so that's one of the triangles. I'm also going to break this down do another triangle that we're going to solve. Okay. But pen doesn't like this table. All right. So these are the triangles we're going to solve. Okay, we have 3 of them. The green doesn't show up very good on the screen. All right, so we have 3 triangles there we're going to solve. So what should we solve for first? I think I'm going to try to solve the length of A to C first. Okay? Because that's going to be the easiest one. We have a bearing in distance and a bearing in distance. So we'll be able to figure out this interior angle here. Okay, so then we'll have side, angle, side. And then we'll be able to solve that distance and bearing. Okay. The other thing we could do there, though, could be a more simpler way, I guess you could figure it, is we could assign coordinates to these 3 points, A, B, and C. Matter of fact, let's do it that way. So, A, I'm just going to arbitrarily pick out a coordinate for A. So I'm going to take and assign A a 1,000 coordinate, okay? That's just arbitrary, you can pick one, it doesn't really matter. And then I'm going to do the calcs to get me up to figure out what B is. Now, to do the calcs, we need to know the change in latitude and departure to find B, okay? So my change in latitude added to my coordinate is going to give me my coordinate for B. My change in departure added to my easting will give me my easting at B. All right, so I've already done that. I will take and give those coordinates out right now. So we have a 1133.02, and that's in the north. 02. And the easting is 1064.88. Okay. And then for C, I figured out those coordinates as well. Northing is 1208.23. My easting is 975.25. Okay? So I figured coordinates there. Now, it's pretty easy to figure out this bearing and distance based on these coordinates. Okay. So how do we do that? Well, we're going to need those. We're going to need to do the arctangent of the change in latitude and departure. So let's see here. We have the change in latitude between those 2 points, between A and C. Actually, A and C. Change in latitude between A and C. Okay, so I have 1208 point, actually I'll do A to C. So A is 1,000 for the northing. Okay, and let's subtract 1208.23 in the northing. Okay, so that's a change in the latitude. If I subtract those, I'm going to get 208.23. If I have the change in departure of A and C, I'm going to have 1,000 in the easting, and I have 975.25 as well. So if I do the change between those, it is 24.75. All right. So in order to find the bearing with these values, by change in departure and change in latitude, I have to do so the bearing is equal to the tangent inverse of the departure over the latitude. Okay? So tangent inverse of departure 24.75 over the latitude, 208.23. That's going to give me a bearing of 06 degrees, 46 minutes, 42 seconds. Okay, what direction is that heading? Well, if I look at my drawing here, it's heading in a northwest direction. Okay, so it's northwest. So I'm going to go ahead and label that on my drawing here, so we have it. Okay, we have a north of 06 degrees, 46 minutes, 42 seconds, west. All right, so now that we've figured out these values, we can also figure out our distance between those, and that's the Pythagorean Theorem. Okay, so basically all we're going to do is take the change in latitude squared plus the change in departure squared. I'm going to take the square root of that, okay? And that will give us, hopefully, the correct answer. So 208.23 squared plus 24.75 squared. Okay, so this is for the distance. Okay, so our distance is equal to 208.23 that gives us a distance of 209.695 or 209.70. Okay? So our distance here now then is 209.70 feet. Okay, so we solved that distance. So we have that part. We're good there. Okay? All right, so I'm going to flip to another sheet of paper. So we just solved for length A to C and bearing. Okay? So let's solve for some other stuff here. We're going to try solving for, so we figured out this triangle. Now we're going to need to take and figure out probably one of these two triangles, but the cog in the wheel that we need to solve for that, to figure out either one of these two triangles, is this line right here. Okay? This line right here is really important to solving the rest of this. And there's one thing that we do know from RP to D, because that's on the curve, this distance we know, it's 155 feet. Okay, from here to here, that's 155 feet. Okay. All right. So let's go ahead and we'll solve from RP to C. All right. So RP to C. We're going to go RP to C. Full length. Your length RP to C. So what we need to be able to do first here is to be able to solve that length. We have to be able to calculate the angle of A RP RPCA is the angle that we have to, or RPAC, that's what we want. RPAC, we need to figure out what this angle is here, okay? Well, that's pretty easy to do because we have the bearing, and we have a bearing. So we can just figure out that interior angle. I have it figured out already. It's 83 degrees, 07 minutes, 33 seconds, okay? So that's that interior angle here. It's basically the difference in these two bearings, okay? So I figured that out. Now that I figured that out, I can go through and figure out the length of RPC because I have a distance here, I have my angle, and I have a distance here. So side, angle, side will give me this, okay? So I'm going to do the law of cosines. So I'm going to say that RPC is equal to the square root of a squared plus b squared minus 2ab cosine of angle A. Okay? So we have that. My side A is this plus this. So I'm going from RP to A. It's 155. Okay? Side B is 209.70. That's this side here. Okay? So 209.70 squared minus 2 times 155 times 207 or 209.70 times the cosine of angle A, this angle. So 83 degrees, 07 minutes, 33 seconds. And we take that all squared. Okay. Oh, I'm off the page. Sorry, I apologize for that. This is what it all comes out to be essentially. All right, so our answer there then will be for the distance, or distance between RP and C will be 245.39 feet. Okay? So I'm going to label that. My distance here, 245.39 feet. All right? So we have that. Now, we'll keep on going. And we're going to actually solve, because I found that side here. I have a side here. We're going to need to find the angle. Okay? So we have side, side. It'd be awfully nice to figure out this angle, because then it would give us this side here. So let's see if we can find some angles here that'll help us solve this. Okay? Well, in order to do that, we have this angle here. We can solve this angle here. Let's take a look at how we're going to take and solve those angles, or which ones would be best first. Okay, so I like angle ACRP. Maybe we can find that angle. Okay, because we have information for this triangle here. So let's see if we can figure that one out. So let's say angle ACRP. See if we can find that one. Okay. So if I do the law of sines and I look at this and figure out law of sines, it's how I'll be able to find this here. So if I go ACRP is equal to the sine inverse. I'm not deriving this or switching around this formula for you. I already have it switched, so I'm not going to go through it. You guys should know how to swap. Basically, this is what I'm using, okay, to find this angle here. Okay, so we're looking for this angle. All right, so let's plug and play that. So sine inverse B. What is B here? Okay, so let's say that B is this side, 155. 155 times the sine of A. Ooh, what's A? A here is this angle, so it's 83 degrees, 07 minutes, 33 seconds, okay? Divided by this distance, 245.39. All right. Excuse me. Let's figure out that. So this is going to come out into be radians. We want to turn it to degrees, minutes, and seconds, okay, because it's an angle. So I come up with 38 degrees, 50 minutes, 13 seconds. Okay, so at my angle here, then, this angle right here, ACRP, is 38 degrees, 50 minutes, 13 seconds. That's our angle there. All right. So we pretty much solved almost this whole triangle now. Okay. So it's going to help us as we move forward. So the next thing I want to find is the last part of this triangle, which is this angle. And that's a simple one. You just take this plus this, well, 180 degrees, because that's what this triangle should add up to for angles, minus this and this, essentially. Okay? So that angle here, then, should be 58 degrees, 02 minutes, 14 seconds. That's basically this plus this, and you subtract them from 180, and that gives you this answer. Okay, so we just solved this other triangle. So we solved this one and this one now. Now we're working down to go solve this one. Because once we solve this triangle, we'll be able to figure out this distance and our arc along here. All right. So let's go solve that. Okay, so let's take a look at solving angle ABC. Okay, so angle ABC. Or no, let's do BCD. That's what we'll solve first. BCD. So this whole entire angle here is what we're looking at. Okay, from there to there. So all I have to do is figure out the difference in bearings. So my angle BCD is equal to 90 degrees, 00 minutes, 00 seconds by looking at these two bearings, okay? Basically, if I transfer this one down as a back bearing, it turns into a southeast. So I'm 50 degrees from south, and this one is 40 degrees from south. So I just add them both together, it gives me 90 degrees, okay? So angle, this is angle BCD is 90 degrees. I'm actually going to write that in there because I don't want it to be confusing for if it was this angle. Okay? Alright, so then let's take and solve for angle DCRP. DCRP. Okay? We're going to solve for that one next. So angle DCRP, okay? So DCRP is, let's see here, what do we know? Well, we know that this bearing is there. Let's look at this for a second. So DCRP, if I take our bearing of A to C, so this bearing here, A to C, that is north 0.6 degrees, 46 minutes, 42 seconds, west, and I subtract this bearing, okay, so it's going to give us this whole angle here. I'm trying to find this angle, so I'm going to take this bearing minus this bearing, and it should give us the full angle. So minus south 40 degrees west. So I'm going to call this a southeast. Okay. And then I'm also going to subtract this. Okay. So this minus this will give us this little tiny angle right here. So minus 38 degrees, 50 minutes, 13 seconds. Okay. So that angle, that is DCRP, is 0.7 degrees, 56 minutes, 29 seconds. Okay, so that's this angle here. I'm going to write it in there. 0.7 degrees, 56 minutes, 29 seconds. Sorry about that, this is a really small drawing. So 0.7, 56, 29 is that interior angle. All right, so that's important to solve that because it's going to help us solve the rest of this triangle. All right, another angle yet to solve. We're going to go with angle CDRP. Okay, angle CDRP. CDRP. So this big angle right here is what we're looking for. All right, we have a distance, and an angle. So we should be able to solve that using law of sines again. Okay, so I'm going to go with the sine inverse of B sine A over A. Okay, we're going to talk about this here in a second, what angle it is. Okay, so if that equals the sine inverse of 240/39 or 245/39 sine of A. A in this particular instance is the angle we just figured out, this one right here. Okay, that's our angle. So 0.7 degrees, 56 minutes, 29 seconds divided by A. And A this time is the opposite from this angle, so it's 155. Okay, so this ends up coming out to be, let's calculate it quick, 245.39, and then 7 degrees, 56 minutes, 29 seconds. Take the sine of that, times them, divided by 155. And take the inverse sign. And then turn it back into an angle. We get 12 degrees, 38 minutes, 0.4 seconds. Okay? All right, well that doesn't look right, because this angle looks a lot bigger than that. Okay? What we just did, in effect, was figure out this angle right here. Okay? That's what we just figured out. The exterior angle for that. So we need to subtract 180 in order to get this angle. Okay? So we need to take this number and take it away from 180. Okay? So this number away from 180. So 180 degrees, and we'll take 12 degrees, 38 minutes, 0.4 seconds. Subtract the two. And we're going to get an answer that is 167, 21, 56. Okay? So that is angle CDRP. So this angle right here is 167, 21, 56. All right, now we're getting there. So we actually can figure out this angle now, down here. A lot of angles we're trying to figure out, okay? Trying to figure out this guy right there. All right, so let's figure that one out. I'm gonna start on a new piece of paper. So in order to figure that one out now, we just basically add this angle plus this angle and subtract them from 180. Okay, so we need angle, we're looking for angle CRPD. CRPD. So all I need to do is go 180 minus 167 degrees, 21 minutes, 56 seconds, plus, so I'll put this in parentheses, plus 7 degrees, 56 minutes, 29 seconds. Okay? And that answer is going to yield an answer of 4 degrees, 41 minutes, 35 seconds. Okay? So that's what that yields. So that's our angle here. 0.4 degrees, 41 minutes, and 35 seconds. All right. Now we're starting to get down to where we can actually start solving for the things we're looking for, which are the distance from C to D and the arc length of AD. Okay? So C to D we can solve right now because we have all the information for this triangle except for that length. So we have both or two of the sides in all three angles. So there should be no problem. We could actually solve that prior to doing this part of it. Okay? We have enough information. So we're going to do it right now. So let's do distance C to D. CD. Okay? So we can use law cosines for that. So we're going to go a squared plus b squared minus 2ab cosine of c. All right. So let's lay that one out. A squared is going to be 155, okay, 155, this line right here, plus b squared, it's going to be the 245.39, 245.39 squared, minus 155 times 155 times 245.39 times cosine of C. What is angle C in this instance? Well, it's the one we just figured out. It's 0441.35. 04 degrees. 41 minutes, 35 seconds. Okay, so this answer in effect we're going to get, if I go through this calculation, I get 91.79. Okay, that is C to D. 91.79. There we go, we just solved that one. So we have one more thing to solve. Okay, that last thing to solve is the arc length of A to D. So the length along this curve. Okay, we have all this information here that just basically broke it down for us. All right, so let's solve that. We want the arc length. It is AD. Okay. All right, so let's solve for I first. How do I solve for I? Okay, I is from this line to this line. Well, that's all I have to do is add this angle plus this angle, and it'll give me I there. Okay, so that's what I'm going to do. My I is 58 degrees, 02 minutes, 14 seconds, plus 04 degrees, 41 minutes, 35 seconds. Okay, so I equals 62 degrees, 43 minutes, 49 seconds. Okay, so I just solve for I. Because we know that in order to find L, we need I and D, okay, for the formula. All right, so now we have I, let's solve for D. We could have solved for that before too. So D is 5729.58, that's the constant, divided by R. Okay, so what is R in this example, I guess? Okay, R here is 155, okay, this distance. So the radius of our arc right here. So 155. All right, so this equals then, remember this comes out as radians, you got to convert it to degrees, minutes, and seconds. So this particular angle comes out to 36 degrees, 57 minutes, 54 seconds. All right, so now I can solve for L, because L we know is 100 I over D. Okay, 100 times I over D. So 100 I, 62 degrees, 43 minutes, 49 seconds, over D is 36 degrees, 57 minutes, 54 seconds, and that ends up being 169.70 feet. All right, we just solved there for the arc length of AD. Okay, so our arc length of AD we just solved. It's 169.70. There we go. We just solved this problem. It was a long process. It takes a little bit of trig knowledge to think about how you're going to break it down into triangles. And that trig knowledge coupled with the knowledge of how a curve works and the variables of a curve will help you solve a problem like this. Okay? That concludes this video.